Okay, so last class we started looking at, okay, the side's moving, but the screen isn't moving. There we go. We started looking at really Newton's second law, okay? And when you start doing Newton's second law on fluid that's moving, all right, it's called linear momentum analysis. And we still start basically with, right there, the sum of the forces equals ma. All right, you still do that. All right, and but what we end up doing is we have to add kind of these other two terms here. Okay, these other two terms are really the forces generated by the fluid coming in and going out. All right, that's basically what it is. And so up here in this spigot here, we labeled all the forces, pressure, weights, pressure. Then we labeled what's coming in and what goes out of the fluid. And those are the two forces that we have to include. Okay? Because really, I mean, you have fluid moving. If you know the mass flow rate of a stream of water and you know its velocity, that gives you the amount of force that if you shot that on a force sensor, you would read that force. Okay? Same thing with a helicopter. If a helicopter is going up, if you know the speed at which the air is moving up and the mass flow rate of that air, that's basically the thrust that it's creating. Okay? So, and then last class we did this. So we had a engine mounted on a stand or a sting, and we wanted to figure out what the actual thrust would be. Okay, and because this isn't moving, the reaction force is kind of our thrust. All right, so here we have our control volume, which is the black. We have the red thing, which is our engine. We have our pressure forces, and we then did Newton's second law and the x direction or linear momentum to figure out what this thrust force would be. All right, so you have to include all your external forces and include all these momentum forces from the fluid on the right. Questions on that? Does that make sense? So fluid, I mean, it could be air, it could be water, and one of the homework problems, I think it's a snowblower. So snow can still act as a fluid. So you can have snow coming into the snowblower and then it shoots out at an angle. The next time you're snowblowing, you're going to be hopefully thinking about linear momentum. Okay?
I want to get into the warmth.
You want to get into the warmth? Yeah. All right. Then we did this one. Oh yeah, I forgot we did this one. So here we have some sort of water nozzle, and we wanted to figure out the reaction force in the x direction to hold it there so it doesn't move. All right. How many times have you had the shower head at the bottom in your shower? Oh, maybe some of you don't have the tube that hangs down. Yeah, the detachable one. All right, I have one. Sometimes I forget, and my wife turns it on, and then what happens? It shoots backwards, and it goes all over, okay? Well, those all little holes shoot out at some mass flow rate, some force, and then you can figure out, if you know all that, how much force you need to hold it back, okay? I mean, that's all what this is. All right, so let's do another pipe problem, but this one, I'm going to add a page. So this is week 4 then. Day 1. So what we're going to do now is use another pipe problem, but slightly different way of analyzing it because you need a different equation. So let's make a sketch here. that's much better. Oh, I should have been doing that a long time ago. Oh, come on. So the diameter of this exit, D2, and it comes out here at V2, comes in here, V1, and let's make it light green. And how do I write there? L. And the inlet here has a diameter D1. And D1 is the green okay? Yep. We got 9 centimeters, D1. Really quiet this morning. Tired? They're just eager to learn. That's good. 5 centimeters. Kind of something new, right? I don't think you've ever, I mean, you've kind of seen this in forces, but not really with fluids. So there's water in here shooting around this. Oh, and we might as well make a boundary. Can I do dots? No, but I can do this. Oh, I don't want that color though. There. So here is, the black is our control volume. So give me some forces acting on that control volume. At where? 2? Good question. That, okay, at state 1, we cut it. There's a pipe there. So the water comes in. So there's a longer pipe up here. Okay, so we just kind of cut it right here. We know the pressure here, the gauge pressure. Okay, so yeah, there's actually going to be P1 gauge times A1, right, as a force. And then at state 2, it's going to be P2 gauge A2. And we know over here there's going to be some resultant force FR. And we can split that up into components. So we have Fx and Fy. So if we wanted to build like a little stand or design something, we can hold it at that spot right there, okay? The other thing we have is the weight of the water. We're actually going to neglect that, so that would be an assumption that we can write down. You could include it if you wanted to, but it doesn't make a huge difference. And I guess the pipe, right? Because that's the water. You could include W of the pipe. Typically, those are kind of small compared to what the forces of the fluid are going to get. So, other assumptions. H2O is incompressible. So that validates our density. We have 2D flow at steady state. And do you remember beta? Beta equals 1, meaning that V1 and V2 are uniform at the inlet and outlet. And when you do the ANSYS, you'll see that typically a lot of the pipe flows, betas are not 1. The velocity at the outlet or inlet aren't usually going to be the same all the time. Okay? Okay, where do we start? We need to write or find Fx, Fy, and the resultant Fr. So we did our free body diagram. We labeled what's going in and going out for velocities. Now we can start the solution. So we're going to start always with this.
I meant to ask you about the subscript X of those also, but only the X direction that we're concerned with.
On the last problem, it is, but this one there's 2D, so we're going to have X and Y. Yep. And actually, I forgot a heading, right? Newton's second law. So, we're going to have two directions. But what can we cancel first off in that? MA, because that nozzle is, we're going to assume it's stationary. We don't want it to move, okay? Then we have the X direction. We'll have the Y direction. Now, you've also seen the I direction and the J direction, right? X is used for I, so don't worry all that. I'm just gonna, I like to stick with just X and Y. So I'm just gonna rewrite this. It's easier for me. I'm okay if you don't, but if you mess up and you do something wrong, then I'll tell you. Maybe you should have written that down. I like making comments like that on your paper. Like fluid student, intermediate, or not intermediate, the beginning student, fluid students. I know I told them to do this problem just like this. What do? Don't even do it right. Don't even label anything. Oh, these aren't vectors, sorry. Those would be X, right? I got carried away. Now you can write a comment about me. All right. We okay right now? Keep going. Forces in the X. I have positive Fx. I have minus P2 gauge A2. Where's that coming from? Is it over? Sounds like it's over here.
It's all offices out there, though.
Yeah.
Big conference room.
It could be. Maybe there's a conference in there too. What, in the X direction, do we have anything coming in for fluid? We only have it going out, right?
Right.
And what do we call that subscript? 2.
So can you cancel like the N? The M dot? With some.
Yeah, sure.
So that's like.
Yeah, that's 0. Yeah, yeah. I was wondering what you were asking. Yeah, you can do that. Pretty sure this. What about P2 gauge?
What about it?
It's 0.
0. We can get rid of that one too.
How the X direction is weird.
Yeah. Because we do gauge. All right, Y direction. Positive Fy minus P1 gauge A1 equals. And I don't think there's anything going out in the fluid, right?
No.
But it's coming in, so we always keep that negative because that's the basic rule. And then we have m dot 1 times what?
V1Y.
V1y. But what direction is that?
Negative.
It's negative, right?
Yeah. So wouldn't it just make a positive?
It'd make it a positive, yep. Yep. Now. That's good. Okay. So let me just solve for Fy. And if you notice, our directions for Fx and Fy are right. Because if you think about it, the water's shooting out at 2, and what's going to happen if we didn't have a brace there? It would move this way, right? It would cock backwards. So we need to hold the reaction force back the positive direction of Fx. Okay? Good. Now, that's this chapter. To find pressure, to find mass flow rate, you've done that in basic fluids. So, what do you want to find first? You want a mass flow rate? Okay. Can we do something first? Conservation of mass to help. What does that state?
M dot 1 equals M dot 2.
Exactly, because the mass flow rate in equals mass flow rate out. And we'll just call it m dot. And then we can now find, sure, we can find m dot 1, which is rho 1A1 B1. Density is 1,000 kilograms per meter cubed times pi. Oh, I'll break my rule. I don't care. You've graduated. Come on, erase. Is it pi d squared over 4?
Yeah.
Yeah, let's do that. So diameter 0.09 meters squared over 4. And then times 6 meters per second. Did I miss something? 1000 pi d. Nope. And you end up getting 38.17 kilograms per second.
I think that was where we go down the velocity, you know,
Yeah.
V2.
No, only V1.
Yeah.
Oh, did I write that? Not write that in the givens?
No.
Oh, I'm making stuff up. You're right. My bad. I didn't give you V2 though,
No.
but you can find it, right? What direction is V1? It's going in the y direction or the j direction. Yep. So if you wrote it in vectors, it would be 0I plus negative 6j, right? Just for reference for any future stuff.
Wait, are you going to give us velocity and vectors?
I won't. No, but just for future, if someone ever, if you have a engineering from another school, they might do that just to remember. Okay, yeah, yep, we got it. Okay, now we can find V2. So we know that m dot 2 is rho 2 a2 v2. We'll solve for v2. And just to save some time, you get 19.4 meters per second. And just for future two, the area 1, because we're going to need to know that maybe, or if you found it in this area, 0.00196 meters squared, just to have it. Okay, so we go back up to our main equation here. We could solve f of x, right? But we might as well find everything we need for everything and then solve them at the end. The only last thing we're missing is P1 gauge. How do we find that? Close. Close.
You don't have to have atmospheric pressure.
You guys are thinking right. What other? So we're dealing with fluid, right?
Rho RT.
No, no. That's only for a gas.
Oh.
Only for a gas.
Okay.
So I labeled states. I labeled state 1 coming in and 2 going out. What do we know about those 2 points?
Certain distance.
Yeah. So there's what Garrett was saying. There's something to do with G.
Rho GH.
Okay. Well, not quite rho GH, but MGH or something like that. Okay. What do we know that is true from at point 1 and point 2?
The same.
Did it in fluids.
Wait, no.
Second half of fluids. Big, long, famous equation. Bernoulli's, which means the conservation of energy of a fluid is conserved at 1 and 2. So we can use Bernoulli's. Do you remember that equation? P1 gauge, what'd you say? No. Plus V1 squared over 2 plus GZ, not rho GH or MGH or...
The Z's for height, right?
Yes, yep.
That is like gonna be in the given.
Uh-huh. Pretty much, it's almost a guarantee in any problem to use G now, right? You almost don't even need to because you know the numbers by heart. So where's our datum? At 0.2, yep. So that means what? That term's gone? Z1 is 0.8 meters. Did I give you that? I didn't give you L either? Okay. I didn't call it Z2. Do you remember the modified Bernoulli's? Vaguely, David? You, after this, you don't write this down, so nothing in blue, but here, you would add what? H of a pump,
Oh yeah, your head loss too.
and then you got head loss, minor and major, and then the turbine. So that's what you would add right there. But I don't think this is quite right because these are in terms of energy. So you'd have to do some of those. We did every one in terms of meters, right? So, but yeah, you would have pump energy, turbine energy, which you subtract, and major and minor losses. Yep. And do you remember the one of the homework problems where you had a graph to find the velocities? Because you couldn't do it theoretically, because you had v squared. Vaguely. Remember how hard that was? Like, oh, never again. What else can we cancel?
P1G.
No,
No.
P2.
P2.
Why is that?
Because that's zero, gauge pressure, atmospheric. So P1 gauge equals rho V squared over 2 minus rho V1 squared over 2 minus rho GZ1. I am going to factor out the density, so I have to write it 3 times. 19.4 meters per second. 2 in that whole term, not the whole term. Just the top term is squared, minus 6 meters per second squared over 2, minus 9.81 meters per second squared, 0.8 meters. Sure. I don't want to add a device. Someone turn their phone on? Turn something on? Test. Oh, no. Oh, there you go. Don't want to tap. And again, do you know why we do gauge pressures? Because if you add, like, if you look here, at even the Bernoulli's is the easiest way. If we add 100,001 on the left, and we keep 101,000 on the right, and you bring one over, it cancels. Okay? So there's no reason to add more numbers that you don't need to. Okay? It's the same way why we do it in Newton's law. So now we can finish, right? So now f of x equals 38.17 kilograms per second times 19.4 meters per second. Get 740 newtons. And I'll do y direction. 38.17 kilograms per second 6 meters per second plus 162 kilopascals times 0.0064 meters squared. 1268 newtons. Make sure you convert to pascals here. And then finally, and when you do that, you get 1468 newtons. I never did the angle, so if someone has a calculator, could you check that for me? Oh, I did do the angle. Huh. What's that? Yeah, it's pretty good force, right? I mean, it's shooting out. What was the speed? 6 meters? 19.4 meters per second, which is pretty fast. Yeah. Because 10 meters per second is roughly about 20 miles per hour. So that's almost 40 to 45 miles per hour coming out of there. Whew. When you stick your hand out the car window going 30, it's pretty good, right?
Did you have to find David?
No, but that just shows you that resultant force is at an angle of 59 degrees from the horizontal. Yep. So now you have these forces. You can then design whatever to withstand that type of force in those directions.
I feel so fast and slow.
The
30 and 5.
oh yeah. Okay. Let's see. Let's take a break. 5-minute break. So at 15, we'll do one more problem. Okay. All right. So I'm going to pause this. This one I can pause. Okay. So we have water being discharged, and it shoots along this cart at 45, and then shoots out here at an angle. Okay. We're assuming that the water gap along that cart is the same from here all the way up to there. Okay. We know it's not, but this gives a good approximation. Okay. We want to figure out what? Determine the tension in the cord to hold it there and the normal reaction of the wheels on the cart. All right. Give the nozzle diameter, which we're going to assume is the water, and it's given the density of water is 1,000 kilograms per meter cubed. So how do we go about doing this? Exactly. Yep. If I told you that somehow that cart was accelerating with thrust, but we wanted to figure out the tension, we would do a free body diagram on what? The cart? Yeah. Okay. Remember that problem? I think you did this problem. Some of you haven't yet in dynamics that aren't in it. Remember the block sliding down a cart?
Yeah.
Find the tension? Well, it's very similar. So let's first, right now, do a free body diagram. And I'm just going to do, actually, why don't I do this? I am going to, no, I'll just do this. Let's pretend the dot here is the cart. So give me one force acting on this cart.
Or like,
What do you mean by that?
friction. I'm trying to think what it is.
Okay, so we got,
In the X direction, right?
Oh, no.
No, that's
we'll get to there. Weight. Then we have, I think someone said normal. We're going to assume it's, does it say anything with frictionless? No, we'll assume in the X direction there's no friction, okay?
Force the water.
Yes, I'm going to get to that in a minute. What's the last major force? Tension, yeah. Now, the water, because it hits at 45 degrees, has to be how many directions? 2. So we know there's going to be f of x, and I'm going to go down f of y. So this is the FBD on the cart. Now, if you remember the block sliding down the cart, what did we also have to do a free body diagram on in that problem? The block. Well, here we have water, so you have to do a free body diagram on the water. Okay? So here is the water. And then this shoots at 45. And that's kind of where our control volume is. So this is V2, comes in at V1. So I guess we might as well write some assumptions here. Neglect friction, right? I need to plug this in. You know what they should make is power cords that are a little thicker, but they have all this stuff in it. It always hangs down and then it pulls my computer down unless I put it on a chair. New capstone. Actually, we were fishing the other day, and I 3D printed cleat boat covers to fit on his boat because we've broken 2 now. We put the pole down when we're fishing to grab another pole to cast. Well, it goes underneath the cleat where you wrap the rope around to hold on the dock. And then I hurry up and grab the pole, I pick it up and it snaps. So I 3D printed the cleat holders. Well, then we're like, then we can design whistlers to go on those 3D printed cleats. So as you're driving with the boat, you can make some music. So I was like, pitch that to the capstone. Or that, sure. Yeah. Yeah. But I can make some money. Neglect the weight of the water. So what are we missing on the free body diagram of the water? They're the same diameters, inlet and outlet. They're both, okay, sure. I didn't even think of that. Well, what are those going to be?
0.
Yeah, because they're both going to be atmospheric. Do you remember, this will help, let's see that.
The surface of the part.
No, well, yeah, none of that. We'll assume none of that. But good thinking about that. Yep. Let me see if I can find it. Oh, let's see here. Give me a second. Probably be maybe day 6. 8. Oh, look at that. Yep. Maybe the 9. Yep. The 10.
So should we look for like the water, we're not worried about gravity on the way?
Yeah, don't worry about that. Yep. Nope. See, when I did this, it was like week 11. See, some of this stuff you're going to cover. Nope. It's kind of nice to have. Maybe I never, did I not cover it? Hey, there's that problem. I don't have it. So, what I'll do... Yeah. Is that this problem? I scroll down that fast? So the other forces, I'll draw them and we'll talk about it, are the reaction, the equal and opposite forces that it's created on the cart, right? Because there's two things. There's the water and then the cart. The water creates all reaction forces, just like kind of like a normal force would, right? If you did a free body diagram on the floor, it'd be going up for normal force. So you have to include those for the water. They generate those forces, okay? Yeah, oh, did they? Sorry, I missed. You did? Okay. Okay. And it's this, remember when we did, this is I was trying to find, I'll show you. If you remember from basic fluids, this was water. This was a gate here. We wanted to figure out what level of water to open the gate. But when you do a free body diagram on the water, you have forces, and those are equal and opposite on the gate. It's the same concept that we're trying to do here. Okay? All right, good. Now we have everything. Let's do Newton's second law on that first. Hopefully, by the time you're done, you've memorized this equation, right? You can cancel that. We have negative fx. What we'll do is you can cancel in the sketch your pressures. So I put red lines through the sketch. Because we know they're gauged, you're going to be 0. Then you don't have to worry about adding those. I'm fine with that. So negative fx and anything coming out, there is, right?
Yeah.
Which is, you write m dot 2, then it's v2x. All right? Okay, and then we do have stuff coming in, right? M dot 1, v1x. So this one has, see how we keep doing examples and keep having different things in there? So now you hopefully have enough. So I'm going to switch the signs. And substitute what V2 is in terms of x. That would be what? V2 cosine? Theta? Oh shoot. I did it again, Joe. You can yell at me. What'd I forget? Got a heading. Y direction. We have f of y equals, oh, let's see here. Oops. We're neglect the weight of the water, so we don't need that.
Hold on, wouldn't f of x be positive to start with and fy be negative? Wait, no. I
Nope.
flipped it on. No,
We're
no,
assuming
no.
positive is this way. Yep.
I don't, no matter how I did something.
Yep.
I didn't switch that.
And in this case, anything coming out there is, right? It would be, yes. So m dot 2 v2y, and there's nothing coming in, so we can put minus 0. And I'm skipping some of the steps just to make sure we cover all the basics. So this would be a sine, right? Is that what I heard? So you use these two, which we find them, to then do what we need to do in the cart.
Is there a reason why the second equation on the f(x) is not a negative number?
I switched it, and so therefore I made that term positive here, and I brought it over to the left,
Oh,
and then I made that term negative. I brought it to the right. Yep. Just easier. Do we know m dot? No, but we can find it. So find m dot. And we'll use conservation of mass, which states m dot 1 equals m dot 2, which is m dot. And it's just rho AV, which is rho pi d squared over 4 times v. Diameter 0.05 meters squared over 4 times velocity. Did I give you that? 12, okay. Now, I don't know why, but they left it in terms of pi. I didn't calculate it either. .5 times pi. I don't know. Someone wants to put that in their calculator, you can tell me what it is, but I can't. I'm not Dr. G. I cannot do that in my head that good. So it's probably going to be what? Yeah, 23, 24 or something? Yep. 5, 6. Thank you. Am I losing anybody? Okay. All right. Do we have everything else? I think so. And now, FX. FX has the movies. 23.56 kilograms per second. I just got to go back up and look at my equation. Times 12 meters per second. And then it was minus 23.56 kilograms per second times, wow, that is sloppy. .56 kilograms per second. Uh, 12 meters per second, but that was cosine of 45. And if you can check, they got 83 newtons. I think that's what I had, right? In last year's notes. And then a y direction, that was just m dot times 12 meters per second times sine of 45. and that becomes 200 newtons. Is that right?
The first one,
First one is wrong?
no, yeah.
Oh, it's right. Check the second one too when you get there. I'll wait for everybody too. I assigned 45. Is that radical? 0.707 or no?
One ninety nine goes
Okay.
yeah.
Okay. And now we can finish it, right? Finally. It's really what we do. We add an extra step to these problems. So now we can do Newton's second law on cart. Sum of the forces in the x equals max. Sum of the forces in the y equals may. Minus t plus f of x equals 0. Then we have normal minus f of y and minus w, right? F of y was down, norm was up, weights, and then equals 0. So t equals f of x, which is equal to 83 newtons. Good. Normal force, Fy, plus the weight. 200 newtons plus 20 kilograms, 9.1 meters per second squared. We get 96 newtons. Make sense? So, just a few things. If we added the weight of the water on the cart, the normal force would go up, right? There's more weight now pushing down. And if there was friction on the wheels in the x direction, they actually help, right? So there'd be less tension, okay? So you could include those if you wanted to, but as long as you understand what we just did here, I mean, you could just add more forces, and that's fine. But you'd use the static coefficient of friction, right? Not the, yeah. So, okay, make sense? So Tuesday, come into the lab. Either go to the AC lab or the computers in the back and work on stuff, okay? And I'll come around like we've done before. You want to work on the chalkboard in the AC lab together, that's fine. Don't matter to me, okay? All right. Have a good weekend.